So today I'm going to speak about wall conditioning. This is the tool to achieve the high performance of the plasma operation and fusion devices. So before I start, so I'm currently doing my PhD. I'm in the fourth year of my PhD. I'm PhD student in the Laboratory for Plasma Physics in Royal Military Academy in Brussels. This is a joint degree. I'm also enrolled as a PhD student in the University of Ghent, related to the topic which I'm going to, I'm working in a few projects related to wall conditioning. The main project is wall conditioning and superconducting Stellarator W7X. I also have side projects in Forschungszentrum Jülich. We are currently upgrading the small toroidal magnetic field device called Thomas for wall conditioning studies and for studies in the field of plasma material interaction. And I'm a little bit involved in wall conditioning studies in JET. So today I would like to explain why do we need wall conditioning. I will talk about the role of impurities in fusion plasmas, about the problem of fuel recycle in fusion devices. I will explain how we can, let's say, deal with these problems. I will talk about different type of wall conditioning. I will give some examples of application of this wall conditioning and W7X. Yeah, feel free to interrupt me during my talk, ask some questions. I try to make my presentation as simple as possible, but when I revise it, it doesn't look like simple. So there will be some technical details, some special terms and definitions and stuff like this. So if it's not clear for participants what I'm talking about, so just please interrupt me and ask particular questions. So I would like to have some kind of free discussion instead of my monologue. Yes.
Yeah. In fact, if I can support what you just said, this is exactly the philosophy of the Fusion EP Talk. We want to have a pleasant environment. We want to have more than a seminar. We want to have a discussion. So, as Andrei said, please participate. And if you, for any reason, your microphone is not working, feel free to type your questions and comments in the chat, and I'm sure Andrei can access it, but otherwise I'll relay it to him.
So should we wait 3 more minutes?
Yeah, I think we can wait a couple more minutes. And at this point, yeah, maybe you could tell us a bit more about, I don't know, your trajectory through Fusion EP, or how did you move on from the Fusion Master, Fusion EP, to your current PhD? What moments in life defined this, or how did you make the choice?
So I graduated from Fusion EP in 2016. So my first year of master was in Madrid. The second year, the first semester of the second year, I studied in University of Ghent, and I moved to Jülich Forschungszentrum for my master thesis. My master thesis was related to development of spectroscopy-based diagnostics to evaluate the reflectivity of mirrors inside fusion devices. It's kind of in situ technique. I'm not going to go deep into details because it's a different topic. Yes, afterwards I continue as a PhD student. So I decided to change my topic because the wall conditioning was somehow attractive for me as business, and yeah, I also was familiar a little bit with what was going on in IPP Greifswald and in Juli Forschungszentrum. So yes, so today is the last day of my third year of my PhD. So yes, in Belgium we have 4 years. I think for experimentators it's an advantage because as far as I know, a lot of people asking, I mean, a lot of PhD students always ask for extension.
But Andrei, where are you exactly based? So, where are you living? Like, are you living in Jülich? Are you living in Ghent?
No. So I live in Brussels because most of the time I have to spend in Brussels, and so I'm a PhD student of Laboratory of Plasma Physics. It's located in Royal Military Academy in Brussels.
Ah, okay, yes.
Let's say
I remember now. Yes.
Let's say 60% of my working time I spend in Brussels. And of course, it depends on the experimental activity on W7X. So last 2 years, I was actively involved. So
yeah,
I spent from 3 to 4 months living in Greifswald.
All right.
And as I told, I have also a side project in Juli Forschungszentrum. So it's almost once per week I go to Juli from Brussels. It's not so far, it's like 2 hours by car.
All right.
1 or 2 days I work per week. I work in Juli. Of course, it depends on the amount of work.
Yeah, I understand.
Nice. Yes, but most of the time I live in Brussels. So okay, I would like to start.
Yeah, that's a good idea. So without further introduction, Andrei, thank you so much for joining us, and I hope you all enjoy.
Yes. So it's time to start today. I would like to talk a little bit about the role of impurities in fusion plasma, the problem of fuel recycling in fusion machines, and a little bit about how to solve those two problems by applying wall conditioning in your fusion devices. So I will explain what wall conditioning is. I will give the example of different types of wall conditioning. And I will also give an example of application of wall conditioning on superconducting Stellarator W7X. I already mentioned what the talk will be about. Again, the role of impurities, the problem of fuel recycling, the need of wall conditioning, different types of wall conditioning technique. Some will go a little bit deep into details for some of the techniques. And I will show the application of those wall conditioning techniques on W7X Stellarator. So I think this is the first slide. Everyone knows what is going on in case of magnetic confined fusion. So as we know, what we need for to confine the hot fuel is magnetic fields. Either we use the tokamak model or Stellarator model. We need some isotopes of hydrogen to fuse, and we'll get some energetic neutrons and helium as a product of reaction as well. So those kind of species, as we see in the sketch, should be the species of our plasma. But in reality, it's not like this. In reality, your plasma is dirty. So you have not only fuel, which is isotopes of hydrogen. It depends which kind of experiments you have. It's not exactly deuterium and tritium. In the current studies, it's also hydrogen and sometimes helium. So you also have helium as a product, and you also have impurities. And this is a problem of fusion. This is a problem of fusion, and in the next slide, I will explain why. So there are two problems which impurity cause in plasma. So first of all, if you have a lot of impurities, you will not be able to have high performance of your plasma. So impurity cause, first of all, radiation power. And depends on the plasma temperature and depends on the type of impurity, you can have different parameters of radiated power. Why is it important? So we need to know and we need to control the amount of impurities, first of all, because those impurities can radiate faster than you heat your plasma. And that will lead to radiative collapse. So the radiative collapse, it means that you don't have plasma anymore. All the power which you inject, say, into the vacuum vessel, which is supposed to be spent on plasma breakdown and the heating on your plasma, can be radiated by your impurities, so you don't have plasma anymore. And you have a termination of your discharge before you want this. And sometimes it can lead to disruptions as well, so which you don't really like to have in tokamaks, for instance. This is the main problem. And for instance, here you can see the different impurities in their influence on the radiation. So first of all, if we take into account only Bremsstrahlung in this case, so the energy loss is proportional to mass discharge ratio. If you have some impurities in your plasma, so the amount of impurities in your plasma can grow because those impurities can be neutralized, they can escape plasma, they can interact with your wall, creating more impurities coming in your plasma, and plasma became more polluted and polluted. So the amount of impurities can grow during your plasma discharge.
So, Andrei, if I may, a question here. So in the last bullet that you have, so multiplied impurities lead to enhanced erosion of the plasma-facing components by sputtering. So let me see if I understand this. So you have certain amount of impurities, but since they are they have a very high Z, so a very high mass, they can be ionized, and then the energy that they impinge on the plasma-facing components is higher. So that now we have higher sputtering rate, right?
Yes, exactly.
Okay.
I think it also depends on the type of wall, no? If I'm not mistaken, like the sputtering cross-section increases not only with energy, but also with how similar the Z are, right? So
yes,
for high Z components, higher Z impurities will have higher.
Yes, I would say that two atoms of similar mass, you would have the momentum transfer would be more efficient if you hit a tungsten atom with a tungsten atom rather than a tungsten atom hits a bunch of oxygen atoms from an oxide or a ceramic or something like that.
Yes, you are right, but we have to take into account here not only physical sputtering but also chemical sputtering, which plays a huge role when when the energy of your impurity species is not enough for physical sputtering. So, and in this case, oxygen is the enemy of fusion plasma because it's really
chemically active. Yes.
So, and if you have oxygen in your plasma, so first of all, it radiates a lot. Second, it leads to chemical sputtering, for instance. So it's you will have a lot of excites if you have oxygen in your plasma. So just like eroded the plasma-facing components, doesn't matter what is it, carbon or tungsten or stainless steel.
Okay.
So
right.
that's a problem.
Yeah.
And I will come back to the second bullet of two main effects related to high performance. So the dilution of hydrogenic species. I didn't put any formula here, but I think we know that we have density limits for tokamaks and for stellarators. I'm not going to go deep into details about different density limits. And of course, density limits depend on the heating scheme and so on and so on and so on. So, but the point is, we have a density limit. If the amount of impurity goes up, so the amount of your hydrogen species goes down, because the total amount should, related to density should be, let's say, constant. It's limited. So you have less hydrogen or isotope of hydrogen in plasma, so you have less fusion reaction in this case, which is also not so nice. So that were two main problems, and I want to say it again, that the main problem, the main impurity which causes a lot of problem is oxygen. We can move further. So the second problem in case of fusion device operation is fuel recycling, and this is a complex problem. So why this is a problem? You have usually hydrogen or isotope of hydrogen as your fuel, and anyway you cannot avoid the interaction of a fuel, like plasma species, some ions and mostly neutrals with your plasma facing components. And depends on the energy and depends on all other parameters, so we will have plenty of effects in the surface of your plasma facing material. So if you look in the picture here, so you have diffusion of hydrogen, trapping, detrapping, some chemical reactions, depends again on the type of your plasma facing material. Especially if you have some carbon, you will have a production of hydrocarbons, mainly it's methane. And it's very annoying because, for instance, if you operate with tritium, you have a limitation for tritium inventory, so you cannot exceed some limits in your future fusion device. So you have to make sure that you have less tritium in your fusion device than the limit is. Yes, and one of the, because of this recycling problem, we also have so-called wall fueling and wall pumping. Depends on plasma facing components again. So you have a standard reservoir in your plasma facing components, and if it's fresh, let's say, and it's not contaminated by any other species, so it can pump your fuel out. So it's called trapping mostly. So you have your fuel, hydrogen or isotopes, inside your plasma facing components. So it means that it's really tricky to control your density. So you inject some gas, you expect to have a certain density, but during your plasma discharge, some fuel is pumped. So the density is lower than you expected. So you have to puff more fuel inside. Another effect, when the reservoir is full of fuel, so it starts to release fuel. And again, when you want to control your density during your discharge operation, the wall itself can fuel because either it's hot or it caused by the interaction with neutral particle, stuff like this. So you have more particles in your plasma than you expected. So again, you have higher density than you expected, and it can also lead to radiative collapse because the density limit is exceeded. So so we discussed more or less those two problems, the problems of impurity and the problems of fuel recycling. And we need to solve it somehow. And one option is called wall conditioning, so which is the tool to improve plasma performance and reproducibility. So this is wall conditioning is a set of different techniques, plasma-based technique, some kind of thin film deposition technique, some mechanical action. and stuff like this. I will explain it a little bit later. So, but the main purpose is to control the surface state of plasma facing components. So it's to remove impurities. If you have hydrogen isotopes, it allows to control isotopic ratio, that you can exactly know how much deuterium and how much tritium you have in your plasma. It can also assist plasma startup. Less impurities here means that you can ignite plasma easily. So as I already mentioned, those radiative collapses, so you can recover after those kind of events. And so of course it leads to more experimental time, so you don't need to suffer of early discharge termination and stuff like this. Yes, now we go to types of wall conditioning. So there are plenty of wall conditioning types. There are some basics, which I will explain it here. There are also some exotic wall conditioning techniques. If you're interested in, you can read about it further, but since we're kind of limited, I would like to talk about some basic wall conditioning technique, which are applied on almost all current fusion devices. So first of all, I personally called it mechanical. It's called baking. I think it's really famous in vacuum technique business. So in order to obtain a good vacuum in the relatively short time, you have to bake your vacuum vessel in order to accelerate the outgassing process.
I disagree with the short time part, because it's usually like a couple of days, but okay.
Okay,
yeah.
accept it.
Yeah.
I mean, in comparison with standard pumping time at room temperature,
obviously,
it's short. That's
obviously, but it's still, sometimes you have to bake it for like you have to leave it for the whole weekend at 300 degrees or something like that at least. So
yes, it's true.
But yeah,
but baking is necessary. So
definitely, yes.
Just coming a little bit back. Why do you have all these impurities in your vacuum vessel? So the first reason, you need to open the fusion device from time to time. You install new diagnostic, you change something inside the vacuum vessel, the components inside the vacuum vessel are exposed to the air for some time, let's say. So, and then you have a lot of let's say dust in your vacuum vessel, and you need to get rid of this. So first of all, you pump your vacuum vessel and go up to a certain pressure, and then either you have to wait or you have to do something with your device to remove all these impurities which are stuck or inside of your plasma facing components. So the first is baking. Then we have plasma based wall conditioning. So you use different type of plasma discharge to clean your device. I think the famous one is glow discharge cleaning. So you apply glow discharge and try to clean further your fusion device. If the glow discharge is not applicable, we also have other types of wall conditioning techniques. Plasma-based wall conditioning technique depends what type of let's say plasma source you have. Either it can be electron cyclotron wall conditioning, so it's based on ICRH plasma, or ion cyclotron wall conditioning, which is based on ICRH plasma. It's pretty easy. And
yeah, Andrei, I have a personal interest in this part, yes, because I'm working on a vacuum vessel with some plasma inside, some cold plasma, and we are having many problems with the impurities created by the plasma. So I'm curious, so you condition the the plasma facing wall by plasma itself. But doesn't that discharge create some impurities that can deposit on top of the wall also?
Yes, and I will come to it later when I will give an example of application of wall condition.
Okay, perfect.
W7X. Yes, it's.
Yes.
I mean, there are problems, there are advantages, there are disadvantages of all this type of techniques. Now, I'm here in this slide I just listed the main types which are like usually applied.
Okay. Thank you. Yeah.
Yes. So another one category is like thin film deposition. Instead of interacting with your wall, you just cover your wall with thin film. That, so can be carbon, boron, or silicon, which will allow you to trap impurities like low Z impurities mostly, sometimes high Z impurities, depends what you want to achieve. I personally divide it in plasma assisted deposition, when you use the plasma to put the thin layer of carbon, boron, silicon, or whatever on the plasma vessel wall, or there are some other techniques like droppers or pellet injectors. So it's usually applied during your plasma experiments. So you can drop some boron during your plasma experiment, which will be distributed by plasma in your vacuum vessel, will have some wall conditioning effect. You can also apply some pellet injection. For instance, if you want to use lithium for your wall conditioning, you can also have lithium pellets, but I'm not gonna give any details about droppers and pellet injectors. So first of all, we don't have time. Second, I'm not a, let's say, specialist in this case. So yes, let's move further. So before I started talking about application of wall conditioning and advantages and disadvantages of different type of wall conditioning technique, so I would like to maybe introduce or remind about the fusion device, which I'm going to use as an example of wall conditioning application. So it's superconducting Stellarator W7X. You can see the sketch of W7X in the slide. So there are a lot of components, and here just to have an idea how complex the device is and how big the device is. So this device was built to demonstrate the steady state capabilities. So far there is no plan to go for deuterium and tritium operation. We are operating in helium and hydrogen only. So some main parameters are also listed in the slides. If you're interested in this kind of details, please check it. So the device was let's say recently put in the operation. So the first campaign was in 2016, and there were also two campaigns in 17 and 18. First in limiter configuration, two last one in diverter configuration. Yes, and the next campaign, so it's not mentioned here, so the next campaign is planned to be in 2022. There will be new diverter installed. It will be actively cooled diverter. As you can see, with passively cooled diverter, we can reach the pulse length of 100 seconds. So the aim of new diverter is reach the pulse duration of 30 minutes. Quite ambitious. I hope it will work, but we will move further. So as I said, so first and last must do wall conditioning technique, it's called baking. So just simply you heat the walls of the vacuum vessel up to the certain temperature. So in case of W7X, it was the whole baking procedure was done in 11 days. And it was baked up to 150 degrees C. Here, So the results of baking immediately shown here. So if we if we look on the residual gas content before and after baking, you can see the reduction of impurities inside the vacuum vessel. So before we could see a lot of high hydrocarbons, for instance. I mean, I don't know how you're familiar with residual gas analysis. So usually we use a mass spectrometry to check what kind of impurities we have inside. So it usually gives some information about the residual gas content. So if we if we simplify the results, so baking always allowed it to reduce the amount of water in your vacuum vessel and to remove all heavy species like high hydrocarbons, some oil left inside, and stuff like this. So if we go a little bit deep into details of baking, as I said, so it was done in 11 days, but the flat top phase of baking was during 7 days. You can see it in the pictures. So different temperature for different components. So if we look on the vacuum vessel temperature, it was the average one was 150 degree. And if we look on the evolution of pressure in the vacuum vessel during this flat top phase, we can find so the pressure dependence. So it means that we can predict the pressure drop and change of residual gas content according to the time. And at least we can say how many days of baking we need, or the reasonable duration of baking, what will it give. And the main point here, that's the pressure drop is not linear, and if we bake even more than 7 days at this 150 degree, at some point it will not improve the situation dramatically. So, but at least here we know the dependence. We know what to do with baking. How long should we bake? Should we increase the temperature, or can we skip it or not? So that was the first type of wall conditioning applied on W7X. The second set of wall conditioning is plasma-based wall conditioning. Here, so main type of plasma-based wall conditioning listed. We can also see the operation windows in case of pressure and plasma density. So first we will start with glow discharge conditioning. So it's based on glow discharge cleaning. It's the common tool to use. I will go into details a bit later in the next slides. So here the point is that glow discharge cleaning cannot be applied in the presence of magnetic field. And for new devices, especially for superconducting devices, when you cannot easily ramp up and ramp down the magnetic field, it cannot be used for wall conditioning during the operation day. And this is a big disadvantage of glow discharge cleaning. That's why you have to go to other wall conditioning techniques like ion cyclotron wall conditioning, electron cyclotron wall conditioning. First of all, depends what kind of heating system you have. Depends on the type of your device. For instance, for electron cyclotron wall conditioning, it depends on tokamak and stellarator, the magnetic field configuration. And most important, it's so-called plasma wetted area. So glow discharge conditioning, let's say, cover most of the plasma facing component during its application. And for instance, for ion cyclotron and electron cyclotron, it depends on the magnetic field configuration, and depends on density, and it depends on neutral fluxes which you produce during this type of wall conditioning. So we start with common wall conditioning tool, which is plasma-based, is glow discharge. Maybe most of you are familiar what glow discharge is, but I would like fusion devices. So glow discharge is ohmic discharge. You apply potential difference between anode and cathode, and you create the plasma. So in case of fusion devices, usually you have a small anode, and the vacuum vessel wall is as a cathode. So you ignite your glow discharge, you ionize the plasma, you accelerate ions towards your plasma vessel wall, and by bombardment of these fast ions, you release the impurities and you pump it out. Again, it depends on type of the device. So glow discharge is not homogeneous, as you can see, because the anode is small in comparison to the surface of the vacuum wall vessel of the vessel. And for big fusion devices like ITER, JET, ASDEX, W7X, you have a few glow discharge anodes. In case of W7X, there are 10 anodes in order to cover by glow discharge more or less the whole vacuum vessel. So you can see also some sketches how the anode is located in the vacuum vessel of W7X. I don't know how informative it is for you, but and how a node usually look like. So we go a little bit deep into details of glow discharge conditioning, and example. As an example, W7X and wall conditioning. So first of all, for glow discharge cleaning, we can use different gases, and actually those kind of wall conditioning glow discharge is sensitive to the type of gas. So usually you apply hydrogen wall conditioning, hydrogen glow discharge cleaning to remove main impurities like carbon oxides, hydrocarbons, oxygen, and water. But at the same time, since we have the problem of fuel recycling, so some hydrogen remains into the plasma in the plasma facing components after the application of glow discharge. So, and it's necessary to apply glow discharge in helium to remove hydrogen from the plasma facing components. So to desaturate your wall from hydrogen after. It's either after glow discharge in hydrogen, or if you operate hydrogen plasma, so it's necessary to desaturate the wall from hydrogen afterwards in order to have a density control in this case. So you usually after baking we apply long glow discharge cleaning, and here you can see the example of so-called initial wall conditioning. So we, in case of W7X, we baked the vessel during 11 days, and then we applied almost 10 hours of hydrogen glow discharge in order to remove the amount of impurities further. So you can also see some kind of trends, and you can see the cumulative effect of glow discharge. So here, for instance, glow discharge cleaning before the plasma operation was done in 2 sessions with break of 1 week. And as I told you, there is a cumulative effect. So you can see that the reduction of impurities follows the certain trends, which we can use to understand how many hours of glow discharge we still need to have before the start of plasma operation, and the relative amount of impurities which we still have in the vacuum vessel. And of course, depends on the type of plasma facing components. Depends, you have tungsten or you have carbon. You can also see the evolution of particular impurities, for instance, how the reduction of water content goes down, or the behavior of hydrocarbons in case of you have carbon-based plasma-facing components.
Andrei,
Yes. Yes.
can I ask a quick question? So what are the sources of those different impurities? I believe in W7X there's carbon plasma facing components here and there. But so one thing, for example, that I note is if I'm, getting the colors right, which is not a given, there's a lot more oxygen seemingly in like water or carbon monoxide than just, molecular oxygen. So I don't know, could you maybe explain a bit on the sources and on, I don't know, how the...
Yes. So the sources of impurity, the first source is that your vacuum vessel, the components inside of your vacuum vessel at some point was exposed to air. So in current fusion experiments, so usually you have upgrades of your device. So you install some diagnostics, you remove something from the vacuum vessel, you install some components inside your vacuum vessel. So you have to open it. It means that the components of the vacuum vessel are exposed to air. So and some of the material inside can be oxidized. Then you have some hydrogen accumulation, some other dust accumulation in your wall. So everything which comes from air is on your wall. So you close your vacuum vessel, you pump it down, you still have some impurities on the surface or in the bulk of your plasma facing components. So in order to speed up the outgassing, you apply baking, but baking is not really effective. So either you have to bake it for really, really long time to get rid of most of the impurities, or you have to apply something else which is more powerful. So which is in this case glow discharge cleaning. And glow discharge cleaning hydrogen, because hydrogen effectively removes all the impurities which you can see in the sketch. So it's necessary to apply it for a certain period of time to remove the impurities further after baking. So baking will not solve all your problems. So baking is really good for like start vacuum conditions. So in order to reach high vacuum, but when you start your plasma operation, you have again interaction between plasma and walls. So and due to this interaction, all the impurities which are like deep inside of the bulk or which were not removed by baking, so they're coming out. And this is not really nice effect because it leads to radiative collapses, plasma disruption, early discharge termination, and so on. So those source of impurity, the main source of impurities is, let's say, air. Then you also have some leaks. So you cannot avoid leaks if your vacuum system is huge enough. So you can compensate leaks by amount of pumps and the total pumping speed for your vacuum vessel. But again, there are some leaks. You have some impurities coming inside the vacuum vessel. It's redeposited in the plasma facing components. So from time to time, you have to apply wall condition to clean a little bit. Then you also have plasma operation, and you have chemical sputtering, erosion, and stuff like this. You also create some impurities. So for instance, in case of CH4, you have some carbon-based plasma-facing components. So, and CH4 is mainly produced by the interaction of hydrogen with carbon tiles due to, so. Yes, that's the three main source of impurities in your fusion device.
So I guess what's also tricky here, now that I read it a bit further, is that you have the intensity of the mass spectrometer in arbitrary units. So it's the relation to partial pressures is complicated to establish, but I guess not so clear. So But do you have an
Okay.
idea of
Usually,
what kind of pressures that represent?
usually that's partial pressures. So here it's intensities, because at that moment mass spectrometer was not absolutely calibrated. So we can see the relative change of impurity amount in the vacuum vessel, but in the real experiment should be calibrated, and you should know the partial pressures, and you you compare those partial pressure to the base pressure inside your vacuum vessel, and you can say something about the amount of water which you still have there, amount of oxygen, and other species.
Yeah, Andrei, I'm curious about how accurate is this this relationship between the intensity that the RGA shows and the actual partial pressures, because in my case we also have an RGA, but we don't really trust this equivalency from total pressure to partial pressures as a function of the intensity of the peaks.
That's a huge topic.
I see what you mean. Yes, it's tricky. So I think it's kind of order of magnitude. So actually, the error bar can be really high.
Okay. Mm-hmm.
I mean, RGA is not really precise. There are more, let's say. Okay, let's say what you mean by RGA. So in this case, it was only mass spectrometer, but there are some also additional techniques. So combination of mass spectrometry and.
In my case, it's a quadruple mass spectrometer.
Okay. I see. Usually there are like few diagnostics, and you correlate the signals from those diagnostics and try to obtain the more or less realistic picture. So that's planned for either. I don't think that there is something like this installed in other devices.
Mm-hmm. Okay, thank you.
I mean, in principle, there are calibration coefficients also for mass RGA, if I'm not mistaken, and then you can like take some kind of pressure valves and do the calibration yourself by sort of injecting some gas controllably by a mass flow controller, and then you can adjust those coefficients for yourself if you want to have that sort of empirical calibration to get that relation.
This is the easiest way. So for instance, for main gases, for instance, you can calibrate it for sure for hydrogen, for helium, for deuterium, whatever gas you have.
Yeah, but there's a lot of things. Well, from what I learned from my short experience in the master's thesis is, well, the RGA itself typically is calibrated against nitrogen, and then there's some relative coefficients that are sort of built in with the device. But then there's a lot of things that can go on that can, in the end, make your measured value not so representative of what's actually going on in your chamber, depending on how you connect the mass flow controller on, I don't know, the pumping, or like what are the characteristics of your wall, and sort of how particles are sticking along the walls along the way.
Yes.
Also on the intensity of your of the current that you put on the RGA filament will change the ionization, the sort of average ionization states of different species in different ways. And yeah, you got to be very careful.
I mean, it can be really complicated. For instance, for W7X, it's super tricky to calibrate it because, so first of all, the mass spectrometer is allocated in the pumping duct, so it's few meters from the main vacuum vessel. So it's differentially pumped. So we have to take into account all the conductancy of the pipe for different species, all this, what you mentioned before, plus, so there is influence of magnetic field on quadrupole, so it has to be properly shielded. Yeah.
It can be as complicated as you want it to be, depending on your application.
Yes. But in my case, I'm studying wall conditioning, so I don't go deep into details. So my primary aim is not to develop the mass spectrometry system. I'm trying to use all the data which is available and somehow connect it to what we have. Yeah.
Anyways, maybe we should go on because
Yes. So yes, so glow discharge is really nice, but anyway, it has to be optimized for every, let's say, for every fusion device. As first of all, so it should be homogeneous, because if the discharge is not homogeneous, it's localized, so you can clean only some special area, the plasma wetted area, so that's so called. So glow discharge has to be homogeneous in this case, and those systems are developed. The glow discharge system usually developed especially for certain devices. That's why there are, for instance, few electrodes in big devices in order to cover a larger area in case of glow discharge cleaning. And so discharge stability, it's also important, and removal efficiency. I mean, removal efficiency, so you can play with glow discharge parameters. Mainly it's glow discharge voltage and glow discharge pressure. And when you find the right set of those parameters like voltage, pressure, you can get the maximum removal efficiency, avoid sputtering, because glow discharge can cause sputtering and plasma facing components erosion, and have a more or less stable discharge. So for instance, in case of W7X, we have some problems in case of glow discharge ignition. So probably you guys familiar with so-called Paschen curves. So the relation of pressure, distance between anode and cathodes, and voltage. And this curve shows the points of breakdown. And in case of W7X, so we can ignite glow discharge in really high pressure, and the glow discharge is not stable. And you can see in the picture, so at high pressure, it's located on the cavities. So it means first we have some arcing, and it's in the, so it's concentrated in some cavities and in the vicinity of anode. So we have some sputtering, which we would like to avoid, because if glow discharge is not optimized in this case, we like not cleaning, we like put more dust. Let's say we erode plasma facing components and redistribute all the things around the device. So in case of glow discharge application, we also have to be careful. So that's why the optimization is needed for every device before you start the routine operation, let's say.
One short comment on this slide. I think another point that you could have added, but maybe it's not relevant to your case, but it's something interesting I read on a poster in ECMAT. Sometimes you can also change like the working gas. So depending on if you're considering also the chemical erosion. For example, there was this scheme developed in CMAT about doing actually nitrogen glow discharge cleanings to try to scavenge out the tritium as a tritium extraction method to avoid inventory.
Yes, you're right. So you can use nitrogen, you can use argon, but again, so it depends. For instance, in case of W7X, we are not allowed to use argon because people are afraid of strong physical sputtering of stainless steel components, and even with helium. If the parameters of glow discharge is not optimized, so there are some sputtering, and after the application of helium glow discharge, people could see the traces of stainless steel components in the plasma. So meaning also not so nice. So it's also impurities. So it's also high radiative species. So it's necessary to be careful. It's necessary to find, let's say, right parameters, right gas, and the application time itself. So if it's more or less clear in case of glow discharge, I would like to move further. So the disadvantage of glow discharge is the following. The glow discharge cannot be applied when the magnetic field is present. So if the magnetic field is present, you will have so-called magnetron discharge. So it will be localized, depends on the magnetic field configuration. So no homogeneity at all. and it means global discharge cleaning is not applicable for, let's say, during the plasma operation days for superconducting devices, because it's not possible to ramp up and ramp down the magnetic field in superconducting magnetic field cores relatively fast. So it usually takes half an hour to ramp up, half an hour to ramp down. And if you need to apply wall conditioning in between of your discharge, between of your plasma experiments during the experimental day, that's kind of waste of time. So then you have to develop different types of techniques, and usually those type of wall conditioning techniques, which is based in plasma, so depends on the heating system. So again, fusion devices are different. Some of the devices have electron cyclotron heating. Some of the devices have ion cyclotron resonance heating systems. Some of them have BOS, which is nice. Yes, here I would like to talk only about electron cyclotron resonance heating wall conditioning, because in W7X, so there is only one heating system, the main heating system, it's ECRH so far. So the ICRH system is foreseen to be installed, but it will be maybe in 2 years. So that's okay. We have to use the tools which are available for wall conditioning. There is let's say, shortcuts of, if someone interested in details, the parameters of electron cyclotron heating system on W7X. So power, frequency, modes, and absorption coefficients are mentioned. There are also some sketches where the launchers are located, just to have an idea how it goes, how it works. And there is also a picture of typical ECRH discharge on W7X, to have an idea how it looks like. So, as I said, in particular in W7X, it's not possible to use glow discharge during the operation day. And if you need to clean your walls, especially to solve the wall fueling problem, so to solve the problem of fuel recycling in your vessel during the experimental day when the magnetic field is present. So in case of W7X, we use electron cyclotron resonance heating. So, and the main problem is wall fueling. So, meaning that we need to use helium in order to desaturate wall from hydrogen. So, we discovered two types of helium ECRH wall conditioning. So, one is so-called recovery discharge. It's just a single long discharge in helium. The same magnetic field configuration, more or less, the same parameters, similar to main plasma experiments with hydrogen, but in helium. So the idea behind the application of helium electron cyclotron wall conditioning is to create high neutral flux, which will escape the plasma and will interact with plasma-facing components, releasing the hydrogen out of it. So there are two types in case of W7X: long single discharges, just long discharge up to 10 seconds with different power, and so-called pulse train. So it's a sequence of short pulses, fixed duty cycle, meaning so we have a certain pulse length, we have a certain interval, and we have a certain amount of pulses in the pulse sequence. Why do we need to use pulse train? So again, fuel recycling is a complicated process, and if you have a long discharge, you have effect of trapping and detrapping, redeposition of fuel which was released from the wall. And in case of sequence of short pulses, we reduce the redeposition rate. So meaning we release some hydrogen from the wall during the short helium discharge, and we have time to pump it down. So this is the advantage of pulse trains. So we tested those two wall conditioning techniques, and we try to compare what is more efficient. So if we go to the next slide.
Can I ask a
Yes.
quick question?
Yes.
It might be a bit of a stupid question, depending on, I guess, your answer. But what's the difference between, if ECRH is the only heating method on W7X right now, what is the difference between ECRH pulses as glow discharges with helium or say with hydrogen, and a so-called stellarator discharge with hydrogen? Because in the end, there's no transformer effect in the stellarator, so I guess I've never seen the operational steps of a stellarator, but I guess you have the standing magnetic field, and then you just sort of excite a plasma and try to heat it. So in that sense, an ECRH, pure ECRH hydrogen glow discharge is somewhat similar to a stellarator operation with ECRH.
It's exactly the same discharges with less power, and in this case, helium, the main discharges. So there are no changes in magnetic field configuration. So because the magnetic field configuration is usually set in the beginning of the day. So you have one magnetic field configuration and you don't change it during the day. So those discharges are operated in the same magnetic field configuration, just slightly with different parameters and different gas.
Is there a very big difference between different, I guess there should be, between different magnetic configurations in terms of how well your ECRH is going to perform, your EC wall conditioning?
In case of W7X, charges are similar, but in case of other devices, you can have different flexibilities. So for instance, if it's possible, you can go from one configuration to another configuration to increase plasma wetted area. In this case, and you go from one type of discharge to another type of discharge, play with it and try to understand what is the best to desaturate the wall from fuel or to remove impurities. I mean, there are plenty of variations. You can have pulsed wall conditioning, you can have different magnetic field configuration, you can have different type of discharge and stuff like this. Yes, in other devices it's possible. In W7X, no, we are limited. I hope it's clear for you. Maybe.
Yeah, I guess those are things that you're also investigating for Ghent. So there's maybe no definite conclusion on it. Like say, if the magnetic field structure is set at the beginning of the day, you could say, okay, today is the day we're going to do our weekly conditioning or our weekly discharge conditioning, and we're gonna, therefore operate this configuration today. I don't know. I guess if I had to turn it into a question, is have you already determined which configuration is more beneficial?
Yes, we can say depends on which configuration is more beneficial. But since we cannot change magnetic field configuration during the operation day, so it's let's say it's useless.
Okay.
So the point is not to touch magnetic field configuration. The point is to play with the discharge parameter, the heating power, the discharge length, the fueling scheme, and some other parameters. But those things are quite exotic, let's say. So there are some parameters which you can change and get better efficiency, gain like plus 30% of cleaning efficiency in case of your cleaning discharge. Or if you change some other parameters, you can gain +1, +2%, so which is not so sufficient in this case.
And how important would you say the wetted area must be important?
The wetted area is important. It's again so it depends on the type of your device. So the idea for some small devices is to create high neutral flux, so that the plasma in this case should be not fully ionized. So you need to have a lot of neutrals in your plasma, and so then the plasma wetted area doesn't play any role when you have a lot of neutrals coming out of your plasma, because so it's more or less the neutral flux is more or less homogeneous, let's say. But in case of W7X and big machines, so the plasma wetted area plays a lot of role, because your main interaction area is diverter. And in case of, for instance, in case of W7X, what we found out that with this type of wall conditioning, with ECRH wall conditioning, so we're cleaning mostly the diverter area. So, and in this case, the plasma wetted area plays a lot of role. So, and we need to increase it. And this is the difference between ECRH and ICRH wall conditioning. So, if we have two heating systems, so ICRH is beneficial because the plasma wetted area is larger in comparison with ECRH. But this is when you have those two heating systems. Yeah, just coming back to my slides. So we try to understand what is better. So single recovery discharges or pulse trains, so the sequences of short pulses, which we can apply. And in the next slides, we have some results. So we use the mass spectrometer accumulated pressure as a, let's say, the measure. So here it's just the relative amount of fuel which was removed according to the time, the application time here. So first of all, we compared different type of recovery discharges, so different duration and different power. We found out that it's better to have as long discharge as possible and with the maximum heating power. And then we compared this, the best recovery discharge with pulse train. And we found out that the pulse train is more efficient if we apply, again, because in case of application of pulse train, we reduce the redeposition rate. So we minimize the redeposition of fuel which was released during the application of wall conditioning. So in case of W7X, depends again on configuration, different parameters. It can be from 30 to 50%. And in case of really bad wall conditions, so the pulse train can save you from the radiative collapse. Again, if you have long high power discharge, it can terminate because you cannot control density, or because disruption, or because of radiative collapse, or because some other reasons. So those application of short pulses is, let's say, is safer in this case. So here I just want to show you the results of pulse train application. So usually you would like to control your density in the discharge. So it's okay if you want to operate at high density, so less problems of wall fueling. But imagine if you have to operate your discharge at low density, and you have the problem of stall wall fueling. So meaning that you inject some gas, you expect to have one density, but it's 2 times higher, 3 times higher, which is not nice for your experiments. So for instance, here, as shown in the picture, we have 2 reference discharges. So before application of helium pulse trains and after application of helium pulse trains. And for both discharges, we had the feedback density control. So we aimed to have a density control of 3.8 10 to 19. And so when we had saturated wall with hydrogen, so we could not reach it because we had straw wall fueling and the density was almost 2.5 times higher. So we needed to apply wall conditioning in this case to desaturate wall from hydrogen to get back the density control. And you can see the density evolution on the picture here below. So first reference discharge, which is green. So we have really high density, which is 2.5 times higher than we expected. Then we applied 2 pulse strings here, and you can see how density goes down from pulse to pulse, meaning that we are cleaning the wall from fuel. And in the end of after the application of 2 pulse string, we can see again the reference discharge with the density close to what we wanted to have in this case. So also that was an example of helium E-series pulse string application as how to get back the density control if you have a problem of strong wall fueling. So we finished with plasma-based wall conditioning technique, and so the next and the last step here is to discuss about thin film deposition. So besides glow discharge, besides baking, and maybe some other how to say, specific wall conditioning based on two previous techniques. So we also can deposit some thin film of carbon, silicon, boron, some other material on your wall, and so first it can suppress the sputtering and erosion of your plasma facing component in case of you have high Z metal and tungsten. So second, it can help to reduce low Z impurity concentration in your plasma, and in particular oxygen, because oxygen is the enemy of your plasma. So meaning that you can trap oxygen, for instance, by application of boron layer, so it can form this non-active, let's say, stable boron oxides, and you reduce the oxygen content in your plasma. And depends on your device again, it can reduce the hydrogen recycling, so it can partially solve wall fueling problem in this case. So based on experience on previous device, there are, let's say, 3 main techniques: carbonization, siliconization, and boronization. So you apply, so you cover your walls by carbon, silicon, or boron layer. So usually in this case, glow discharge is used. So you apply glow discharge in the mixture of gas. So there should be carrier gas, it's usually helium, and it should be reactive gas, depends on the type of film deposition you want to apply. So usually the thickness of the deposited layer is from 50 to 100 nanometers, which is enough to have a stable operation of your plasma without any problems with radiative collapses or disruptions. But it again, it depends on the type of your device. So it's the lasting effect for tokamaks can be 1-2 operational days. In case of Stellarators, for instance, example W7X shows that it can be 1 month. So on W7X, we applied boronization. So it means that we covered our walls by boron layer. So there were 3 burnizations done in the last campaign. We used glow discharge and mix of diboran and helium. So it was 10% of diboran and 90% of helium. Depends on the procedure. So was from 3.5 to 5.5 hours. And we are not sure still about the thickness of burn layer, which was so according to, let's say, last investigation, it was from 50 to 70 nanometers. So, but this information is important when you want to understand the erosion rates of burn layers. So in case of advantage of burnization, it was, in case of W7X, yes, it was really successful. So first of all, due to reduction of oxygen, we could reach high density. So usually it was before burnization, it was not higher than 5 times 10 to 90. In case of hydrogen plasma, so after the first burnization, we could reach something like 10 to 20, so which opens some space to investigate new effects on W7X Stellarator. Yes, we can also see that the first burnization reduce the amount of oxygen, and oxygen was also a problem for which caused sputtering of carbon. So we reduce oxygen, and by reduction of oxygen, we also reduce the amount of carbon in plasma. So we could run plasma discharge in hydrogen with high density, and so we reach the duration of 100 seconds, which was not possible before the burnization application. So also here you can see that because we reduce oxygen and carbon content, so we also reduce the combination, so which means that the chemical sputtering plays a huge role. So we can see that hydrocarbons and water the amount of water was reduced by burnization here. So yes, burnization was really successful in case of W7X. So I hope I explained more or less clearly different types of wall conditioning technique, some examples of application on W7X. So what I want to say now is that for different fusion devices, you have to find a different wall conditioning strategy, meaning that you have to find the right wall conditioning technique, how to apply it, which parameters to use, how often to apply, and the consequence of application. For instance, on W7X, we divided wall conditioning steps in two. This was initial wall conditioning, was wall conditioning applied before plasma operation. So we pump down the vacuum vessel, we bake it, we apply the first glow discharge in hydrogen to remove impurities, and then in helium to remove hydrogen. Then we started our plasma operation. Before we applied before we started with burnization, we also used glow discharge cleaning in hydrogen to remove impurities, in helium to remove hydrogen. So then we came to application of burnization. Burnization solved a lot of problems. So burnization reduced the amount of carbon and oxygen in our plasma. So it allowed us to operate at high densities, long discharges, high power. But burnization didn't solve the problem of didn't really solve the problem of wall fueling. And when the wall was saturated by hydrogen, so in case we could not control the density during the plasma discharges, so we applied pulse trains in helium. So helium ECRH wall conditioning to desaturate the wall's plasma facing components from hydrogen and to get back the density control. So few ionizations were applied, and helium ECRH wall conditioning were applied when it was needed, when there was a problem of strong wall fueling. Yes, that's a kind of strategy for W7X for next campaign. If there are no changes in case of type of plasma facing components, and in case of different, let's say, heating techniques. So if there is an installation of ICRH system, we should also test the new wall conditioning techniques. So based on ICRH and compare it with ECRH wall conditioning techniques. So new installation will cause will enforce us to investigate further the application of wall conditioning in this type of device. Yes, and finally I came to the end. Maybe I will repeat again. So then instead of summary, this wall condition is necessary tool for high plasma operation. So if you want to have high plasma performance, you should definitely apply wall conditioning, and you don't need to skip it, because I mean, it's always clear that the wall conditioning should be applied, but some people think that, okay, this is kind of routine operation, it takes some time, and we would like to skip it in order to have more experiments related to studying new physics and device optimization. Unfortunately, it doesn't work like this, so people should think about wall conditioning. So as I discussed, there are a lot of wall conditioning techniques. There are some main wall conditioning techniques as baking, low discharge, ECRH, ICRH wall conditioning. For some devices, you can find some specific wall conditioning techniques. So I didn't discuss, for instance, thin film deposition with droppers and pellet injection. So it can be also used. As we saw, for instance, for W7X, different wall conditioning techniques should be applied at certain time with different frequency, certain parameters. And yes, before you start to use wall conditioning techniques as the routine technical procedure without any physics behind it, so you have to find the strategy and you have to optimize all these kind of things, because wall conditioning can also take a lot of time, and the operation on big devices like Jet W7X will be in ITER, so it's limited. Yes, that's all for today. If you have any questions, please go ahead.
Hello.
Yeah.
Yes, my name is Daniel. Thank you for the talk. I really liked it. Sadly, I don't have much time left, but I want to know, what are you doing at Jülich?
So in Jülich, we are working on the upgrade of toroidal magnetized system called Thomas. So it's let's say toroidal device with only toroidal magnetic field. So there is no poloidal magnetic field. I wanted to include the slides, but at some point I decided not to include, so with main parameters and how they look like. So we are upgrading this device in order to study wall conditioning. So to compare different wall conditioning techniques, to find the optimal parameters, to study a little bit plasma wall interaction, plasma material interaction, and stuff like this, to, let's say, educate students to install different diagnostics.
Yes, and are you currently using all those types of wall conditioning, or just which ones?
So, for example, we have the same low discharge anodes installed in Thomas, and we study we study the glow discharge breakdown on Thomas, because glow discharge breakdown in W7X caused erosion and redeposition of eroded material, and people are complaining that we have some traces of arcing because of glow discharge, so it should be optimized. And since W7X is not operational now because it's under upgrade, we cannot just request some time for glow discharge studies, so we should study glow discharge in some other devices in similar conditions.
Yes, thank you.
Yeah, Andrei, thanks a lot for this comprehensive talk. Could you go back quickly to the one of the first boronization slides? Okay, okay, so I had two very simple questions, I think. So boronization is typically done, I think, with mixtures of helium with boron-rich gases like the deboran that you showed, but also carborane sometimes.
Yes.
You know what kind of carrier gases, or say silicon-rich or carbon-rich gases are used for carbonization or siliconization? Or if it's done differently?
Yes. So since I don't have a lot of experience with this, and so siliconization, for instance, was used long time ago, I will briefly try to check the paper about it.
I don't want to take too much time anyway, so
yes,
I can also look it up.
For those type of wall conditioning. Okay, so I found it. So for siliconization, it's silicon hydride, so silicon H4. There is a nice paper of York Winter. It's called Wall Conditioning in Fusion Devices and its influence on plasma performance. So there are a lot of information about this type of wall conditioning, so with references given. Yeah, it was published in 1996, but still can be used to, let's say, to go a little bit deep into details.
And I suppose carbonization you could do with any volatile hydrocarbon.
Yes.
As long as you don't have too many covalent bonds, so to sort of make it sort of easily breakable.
Yeah, but most of these gases are toxic, so, and nowadays it's not so easy to apply. So the procedure requires a lot of preparation, and especially if you work in Germany.
So that actually leads to my follow-up question, as I understand deboran is quite toxic and quite flammable. So why, if you have plasma-facing carbon, plasma-facing components, why do you need to use deboran and not some kind of benign carborane, like orthocarbon?
So first of all, because there is experience of application of deboran, I mean, the application is really easy. You just need to inject deboran with helium, run glow discharge, and you will coat your walls with boron. Okay. This is one thing. The second thing, so kind of like boron droppers are not so efficient like glow discharge with this mixture of gases.
Oh, but you don't, the carborane you don't necessarily do with droppers. For example, in my experiments or in TJ2, what they do is they have a little oven. It's just a four-way cross sort of plugged into the device sort of and gated. And you heat it, and it will, those carborane crystals, they just evaporate at pretty low temperatures at like 70 or 100 degrees. And then you just have this gas of carborane going into your device, and it's broken down by the helium plasma. That's the usual PACVD process. It's just not toxic and not flammable, really not very reactive material.
But you see, in case of this, it's a little bit more complicated because you have to install this device. You have to install heater, and it also causes some engineering work and stuff like this. So, for instance, in case of boronization, You just need to have glow discharge system and let's say the good exhaust.
I swear to you, it's extremely easy to install. But I mean, you know, like maybe later we can talk about it. I could show you some pictures. It's a very dumb system. But I don't know. The regulations also might make it, you know, complicated. I understand.
Yeah, of course, there are some debates, and yeah, different type of devices can be installed, but usually it's decided by let's say directors of the institute and this kind of financial management who want to invest in one thing and another thing. So
I guess you also have to fight for ports in a big machine like this. So yeah.
Yes. So I mean, it's not so easy. Usually, people, if you say, okay, this is not toxic and this is more, let's say, more efficient, so people will say, how much will it cost? They will ask, and then if they compare, okay, maybe we can go for low efficiency and so with toxic components, but we will pay less and we'll take less time to install, stuff like this. I mean, this is all these technical details are really complicated.
Well, just to say, I actually researched that for fun one day, and pretty much the same amount of iborane and this orthocarborane, like in grams, let's say, it's like 5 times cheaper to do it with the orthocarborane. But anyways, yeah, yeah. Anyway, just mentioning it.
Yeah, sure. But for instance, if you want to install in the big device, if you want to install something, so it's long procedure. So first, everything should be designed, a lot of tests, then commissioning, then like first operation.
Yeah, this part I will not debate. I understand fully.
I mean, this is the main part. It's not because, for instance, carborane is cheaper than diborane. It's not a problem. So the problem is time, in this case.
Yeah, time is the most valuable asset. Okay. Are there any further questions, Francis, Sylvia, Danielle?
Yeah. Okay. Yeah, I have like 2 questions.
Yeah, sure.
Okay. Yeah. First of all, thanks, Andrei, for the talk. Okay. So I have a question on the slide 4.
Yep.
Yeah. Okay. So the figure, in the x-axis, like this figure depends on the electron temperature.
Yes.
So why depends on the electron temperature? The the radiation parameter.
Because I mean, I don't know the formula by heart, but so the temperature is included as well. So
yeah, but like ion temperature makes sense. Like why the electron temperature?
No. This is a temperature of plasma. This is a temperature of your plasma. So I mean, you can recalculate if you know the plasma parameters. You can recalculate it to ion temperature.
Okay. So
this is related to plasma temperature, so which is electron temperature. So it's that doesn't it's not directly related to the ion temperature of the impurity species itself.
I think I can add something on this. As I understand it, Bremsstrahlung, it's a kind of X-ray radiation.
Yes.
And X-rays are typically related to the electron state, whether it's bound or free. And so with increased energy or temperature in the electron, you'll get those mountains, those little peaks that you see there. They actually correspond to the first ionization, second ionization for these different atoms or ions. And eventually what you see is something that's sort of smoother and goes up. And that's basically when you get to very hot plasmas, like for example in the core, where the atoms are fully stripped. And then it's just a continuum because your electrons are just sort of well, it's like pure. So the first part is X-rays due to line radiation, and the second part is X-rays due to continuum radiation or Bremsstrahlung, which is basically just you have faster and faster electrons, so sort of more possibilities to break and to slow down and to be slowed down in Coulomb collisions and to release that energy into X-rays. That's as I understand it.
Yeah. Okay. Yeah. Yeah. Now I understood. Okay. So and then on slide 16.
Yep.
Okay. So so if I understood you correctly, like the ECR heating, the aim is to make the neutrals hit the plasma facing component to remove the hydrogen.
Yes. Okay. Let me say it depends on your plasma. So in small devices, yes. So you create neutrals in order to, let's say, to allow these neutrals to interact with your walls to release some species from the wall. Yes.
Okay. So in, let's say, like in that context, so how the ECRH heating heats the electrons, and electron transfers the energy to the neutral atoms by cohesions, and then they get the high temperature and then they collide with the plasma walls. Is that the process that will happen?
Yeah. So first of all, so you heat your electrons. Then there is plenty of processes in plasma. So electrons collide with ions, they hit ions. Then there is kind of recombination, charge exchange, recombination processes. So, and depends on the temperature. For instance, if the temperature of your plasma is hot enough, so you will get, especially in the core, fully ionized plasma. But if the temperature is not high enough, so the plasma will be partially ionized, and you will have a lot of neutrals still in your plasma. And sometimes this is the reason. So because neutrals can escape your plasma.
Okay. So why we are not using like ohmic discharge to do the same thing?
The trick is that we cannot use ohmic discharge when the magnetic field is present. It's not homogeneous.
It's not homogeneous. Okay. Okay. Yeah. Okay. Yeah. Thanks.
Are there any more questions?
Yeah, like one more question. Maybe it's stupid. Like first of all, like thank you for the nice talk. That was really entertaining and good. My question is, you stated that polarization usually is attempted to be to give a layer between 50 and 100 nanometers. I don't remember the slide number, but yeah, why do you not try to achieve like thicker layers or thinner layers? Like, is there like thinner? I could guess because it wears too fast off, but why not try to attempt thicker ones? I guess in Wendelstein there's no problem because it's fine for months, like you said, but in tokamaks?
So here it depends how long you boronize. You can achieve 200 nanometers, but the time of the procedure should be reasonable. I mean, probably if it's allowed to, let's say, boronize for 3 days, yes, you can do it. But I think there is a time limitation. So again, those gases are toxic and there are a lot of safety requirements and stuff like this. This is one point. The second point, especially related to Wendelstein and Stellarators. So what we found, the erosion rate is small enough. So it's enough to have less than 100 nanometers to have a lasting effect of burnization for 1 month at least. So in this case, we don't need to go for long glow discharge operation.
All right, cool. Thank you.
Yep.
Okay, if there are no further questions, let's thank our speaker again. It was a very good talk, very interesting, and I think it spawned a lot of discussion, which is what we're here for. And I'll hope to see you all in 2 weeks for Johannes' talk on his experience at TJK, sort of revamping a Langmuir probe actuator. It's going to be think very hands-on, very practical. So I think it's going to be pretty exciting too. Thank you so much, Andrei, for
Thank you.
giving this talk.
Thank you for your attention.
And until next time.